Determine the integer for which 2 to the power of x plus 1 is 64. Well, 64, I believe, is 2 to the power of 6. So if we were to just rewrite this, it would be 2 to the power of x plus 1 is equal to 2 to the power of 6. So that basically means that x plus 1 is equal to 6, and therefore x is 5. Determine the value of t and u that satisfy these equations. So again, from this one, t plus u is 8, and from that one, u minus 3 is 2. So if u minus 3 is 2, that means u is 5. And if you sub that back into here, that would mean t is 3. So u is 5, and t is 3. Determine the integers m and r for which this whole thing. Okay, so that means 2m plus r is 7. And what's the other one here? 3m minus r is 3. Okay, so I guess we have to solve these system of equations. Add these two, and we get 5m is equal to 10, and therefore m is 2. And then sub m equals 2 into either one of those, and you get 2 times 2 plus r is 7. So therefore r would be 7 minus 4, which is 3. M is 2, r is 3. And then the last one, show that there are no integers p and q for which 2 to the power of p plus q times 5 to the power of p minus q is 80. Okay, so 2 to the power of p plus q times 5 to the power of p minus q is 80. Now 80, we have to break that down into its prime factors. So I believe that is what, 16 times 5? And 16 is 2 to the power of 4, and then it'll be 5 to the power of 1. So that's the prime factorization of 80. And then this is, again, this doesn't change for now. All right, so now if we match these exponents, that would basically mean that p plus q is 4, and this p minus q is 1. Okay, add them, and we get 2p is equal to 5, so that means p is equal to 2.5. So there we go. Since 2.5 is not an integer, we have shown what they are asking us to, that there are no integers, p and q, for which this holds true. The quadratic equation, x squared minus 2x minus 1, has the solutions x equals r, x equals s. Determine the integers b and c for which the quadratic equation x squared plus bx plus c is equal to 0 has solutions 2r plus s and r plus 2s. Okay, let's see what we can do here. So the first thing I think is just to concentrate on that equation that they give us and figure out the roots. And you guys can do that. I mean, the quadratic formula has been done to death. And when you do, you'll find the roots are 1 plus root 2 and 1 minus root 2. So basically, this is your s, or whatever, it doesn't really matter. This is your r and this is your s, I guess. Okay, so therefore, let's see here. What are we doing next here? Oh yeah, then we have to concentrate on this x squared plus bx plus c equals 0. Okay, so they're saying for this equation, the roots just this time are 2r plus s and r plus 2s. So if I substitute these values in, and I'll let you do that, I'm sure you can, and I'm going to call this x1 and x2 actually. It's very interesting how they wrote the same x. It's a little confusing, but it's okay. x1 and x2, two different roots. So x1, when you put r as 1 plus root 2 and s as 1 minus root 2, you will get x1 is 3 plus root 2. And then x2 will calculate to be 3 minus root 2. All right? So then that basically means that this equation, x squared plus bx plus c, can be really written as x1 minus its first root, or actually what I should be writing, x minus its first root. See, it's important to distinguish that root as something different than x, and x minus the second root, right? That's another way of just writing the same equation. This side does not change for now. That's just going to be x squared plus bx plus c. But this one becomes x minus 3 plus root 2. And this becomes x minus 3 minus root 2. And then when you expand this all out, I'll let you do that. I'm certain that you can. You'll get x squared minus 6x plus 7. And therefore now you match the coefficients, and there you will determine that b is minus 6 and c is 7. So that is part A. Suppose that m and p are real numbers for which the polynomial f at x is x squared plus mx plus p has two distinct positive real roots. Prove that the polynomial g at x, which is equal to x squared minus m squared minus 2px plus p squared, has two distinct positive real roots. Okay. All right, we're going to need a lot of space for this one. So first, I've got this f at x, and that is x squared plus mx plus p, right? And they told me that there's two roots, so I'm just going to call them root 1 and root 2, r1 and r2. And they have told me that these roots have some properties. They are distinct, meaning they are different. They are positive, and they are real. Okay. All right. And then we have to prove, that this other polynomial, which they are saying is x squared minus m squared minus 2p x plus p squared, this has roots that are also positive, distinct, and real. All right, so, okay, somehow, some way, I'm going to have to do that. Let's start with this one here, since that's what really the only thing we have to work with. X squared plus mx plus p has those roots. So it's very similar to the previous question. Another way of writing it is x minus its first root, x minus its second root. Correct? And then when you expand this all out, you will get expand and collect like terms, x squared plus minus r1 minus r2 x plus r1 r2. And this is x squared plus mx plus p. So that basically means if you match the coefficients, this m is equal to minus r1 minus r2, and that p is equal to r1 times r2. Now you could have also gotten that by Vietas. It's your own personal preference how you want to do it. Vietas says that the sum of the roots are equal to, oh boy, what was it again? Minus, was it b over a? Yeah, b over a. No, minus b over a. Yeah. Yeah, minus b over a. So minus b over a, so that means r1 plus r2 is minus m, which is the exact same as just writing it like that. And that's exactly what we got there. And then the product of the roots, according to Vietas, r1, r2, would be for a for this particular polynomial, which is second degree, would be c over a. In this case, that would just be p over 1, which is just p, which is exactly what I got up there. So regardless of how you want to do it, whether you want to do it by expanding the polynomial or by Vietas, you'd get the same results. Okay, so that's some progress, I guess. Now we have to go back to that big one. Okay, so let's go back to that one. Now g at x, so we got g at x is equal to x squared minus m squared minus 2p plus p squared. Okay, so where do we go from here? I guess we have to substitute these guys. Yeah. Okay, let's substitute those in. So x squared minus m, so this is going to be minus r1 minus r2 all squared minus 2, and then p is r1 times r2, and then this I guess is going to be, and what's plus p squared, so r1 squared r2 squared. Okay. Yeah, I think that's right. It seems a bit... Yeah, I think that's fine. Okay, so then this one here, I'm just going to factor out the -1. Yeah, like that. And then just make this r1 plus r2. And this whole thing all squared. It's equivalent. It's just it makes it easier. Because when you then square the -1, it just becomes 1. So then this is just going to be r1 squared plus 2r1 r2 plus r2 squared minus 2r1 r2. And then plus r1 squared r2 squared. So this is x squared, and I believe those cancel, so that just becomes r1 squared plus r2 squared plus r1 squared r2 squared. Okay, let me just see here. Yeah, I think that's correct. Make sure I want to make sure I didn't mess up the algebra, because one mistake and then the whole thing's gone. Okay, so far I think I'm okay. And then, okay, so I have to kind of designate some roots, so I'm going to call them K1 and K2. So very similar as before, this can be written as x minus K1, x minus K2, and it's x squared minus r1 squared plus r2 squared plus r1 squared r2 squared. Okay, so yeah, that is correct. That is correct. So I'm actually going to use Vietas this time. It's just quicker, but you can do the expansion if you wish. From Vietas, the sum of the roots, which I guess would be K1 plus K2, A is equal to minus B over A. So if you apply minus B over A here, it would be R1 squared plus R2 squared. Correct? Yeah, and then the product of the roots, which would be K1 times K2, would be C over A, which is just R1 squared times R2 squared. Correct? Yeah. Yeah. And, you know, another thing I just noticed is that this thing can be factored. This right here, let me use a different color to illustrate what I'm talking about. This equation can be factored into, let's see here, x r1 r2, but squareds like that, and then minus minus x1 yeah. So therefore, if we match these, this matches with that. So K1 is equal to R1 squared, and this is equal to R2 squared. Ah, okay, I got it. So, going back to the very beginning, right here, R1 and R2 were distinct, positive, and real. So if R1 and R2 were distinct, positive, and real, then if you square them, which is basically what all those are, those will also be distinct, positive, and real. They will also be, yeah. And that's what they wanted you to prove, that the polynomial, this big long guy, has two roots that are distinct, positive, and real. So that's pretty much how I would approach that question. Suppose that A1 is minus 6, B1 is 10, and C1 is negative 5 for each positive integer n greater than or equal to 2. Let an be that, bn be that, cn be that. Prove that the polynomial f at 100x has three distinct positive real roots. So A1 is minus 6, 10, and C1 is minus 5. Okay. All right, so the setup is, so this equation they want us to prove has 3, so let me call them R1, R2, and R3, and that they're distinct, very similar to before, distinct, positive, and real, the roots. All right, here we go. So this equation here, well, the one that I guess we have to work with, the basic form, would be of the form x to the power of 3 ax squared plus bx plus c is 0. And I'll just call those roots r, s, and t for now. So therefore, if we were to put it in a form where it's factored, it would be x minus r, x minus x, x minus t, right? And then when we expand all of this and collect like terms, we would get x power 3 minus r plus s plus t, x squared, plus rs plus rt plus stx minus rst. And therefore, this, if we match the coefficients, a would be equivalent to minus r plus s plus t, b would be equivalent to rs plus rt plus st, and c would be equivalent to minus rst. And you get the same result from Vieta's, by the way, in case you want to do Vieta's. Okay, so now I'd like to keep these in the same screen because those recursive formulas are actually very important to this question. They're what will allow us to get this 100 here. In case you're wondering, what is that 100 referring to? It's basically referring to that recursive formula. So first, let's start with I guess with just f1, because these are all ones here. That's 1, that's 1, and that's 1. So that's referring to f at 1. So f at 1 is basically, if this is f at x, right? F at 1 would be a1 x squared plus b1 x plus c. And then they start us off with those the ones. So a1 is minus 6, and then b1 is 10, and then c1 is minus 5. Okay, and then you say, well, then how do I get the other ones, a2, a3? Well, this is what these formulas are. These formulas up here are designed in a way to help you get a1, a2, a3, and all that. Got it? So a2, for example, would be, in this case, 2 times b1 minus a1 squared, correct? So b1 is 10, and a1 is minus 6. So that looks to me like 20 minus 36, so minus 16, if I've done that correctly. And similarly, you do the same for b2 and c2, and that would give you f at the polynomials, or sorry, the coefficients for the polynomial f at 2. You got it, just like how this is f at 1. F at 2 would be with a2 instead of a1, b2, and I guess c2 instead of c1. All right, so we now will discuss this guy. This equation right here. If I were to write that again, that's f at 1x. If I put 1 as a value of x, if x equals 1, this will give me 1 minus 6 plus 10 minus 5 which is 0. So that means that x equals 1 is a root, just with a little bit of experimentation. And then I guess f at 1x, we can factor it as x minus 1, and then if we use long division, you can factor that and get the remaining part as x squared minus 5x plus 5. And then that, use a quadratic, and you'll get, when that's set to 0, x will be equal to 5 plus or minus root 5 over 2. So the three roots of this guy are x equals 1, x equals 5 plus root 5 over 2, and x equals 5 minus root 5 over 2. And these three are obviously distinct. They are all positive, and they are all real. So they fulfill the criteria. And I'll refer to these as R, S, and T. I think I put it up there. So this will be my R, this will be my S, and this will be my T. Okay. So similarly, as we go through this, now using Vietas, we can deduce from all of our equations that an minus 1 would be minus r plus s plus t. Bn minus 1 would be rs plus rt plus st. And Cn minus 1 would be minus rst. But now we have to figure out, using the recursive formulas, the values for just the general an, bn, and cn. So we're going to use these recursive formulas that they gave us up here to figure this out. So here's the calculation. I'll just substitute it in. So if you use those recursive formulas and you grind them all out, you will get that an is equal to this guy, bn is equal to this, and cn is equal to that. And therefore, you can just sub those in and mix and match with this original formula right here, up here. So that would basically mean that f at n, whatever n is, would be x to the power 3 plus a n x squared plus b n x plus c n. And therefore, if we have any kind of number, so if we add these coefficients, you'd basically have x to the power of 3 plus it should be minus actually, minus r squared plus s squared plus t squared x squared plus r squared s squared plus r squared t squared plus s squared t squared x, and then plus cn, which in this case is minus r squared s squared t squared. So if we had, and then we have to now kind of think about this. If we had f1, and f1 we did up here, right up here, and we proved that it had three roots that were distinct, positive, and real. If we use a recursive formula and apply it here and come up with f2, then f2 would give us this scenario right here. Let me see if I can squeeze this into the same screen. Yeah, it would give us this. And this basically, if we're using n equals 2, we would get that the roots, in this case, if we match this up using Vietas, the roots this time are r squared, and let me use the same kind of, well, I don't want to confuse anybody, but these are lowercase. That's what I mean, really should have put. But in this case, it's r squared, s squared, and t squared, according to this polynomial, the roots. And you can come to that conclusion either using Vieta's, or if you really want to, you can sort of expand it all out. So you'd have to go x minus the first root, let's just call it root 1, x minus the second root, x minus the third root, and then expand it all out and then match the values. You'd see that the this part, for example, dot dot dot, it would be like r1 squared, r2 squared, r3 squared, like that. And then you can match that the first root is r squared, the second root is s squared, and the third root is t squared. So what that proves to me is that if these guys are up here, r, s, and t are distinct, positive, and real, then their squares will also be positive, distinct, and real. And then you just continue like that. It would be the same thing for f at 3, f at 4, and so on, all the way down to f at 100. Each polynomial will basically have roots that are the squares of the previous polynomial, and therefore this means that all the roots will always be distinct, positive, and real. In the diagram, ABCD is a rectangle with AB greater than BC. P is on CD so that PD is equal to PB. Suppose that PD is 53 and BC is 28. Determine the length of AB. Okay, so they're telling me that that's 53 and that's 53 and that's 28. Okay, so using quadratic, not quadratic, Pythagorean theorem, PC squared plus 28 squared is 53 squared. So when you solve for this, you get PC is equal to 45. And then what do they want? They want the length of AB. Well, AB is basically DP plus PC. So that would be 53 plus 45, and that is 98. Suppose that AB is 100. If the length of BC is an integer, prove that PD cannot be an integer. So let's draw this diagram again. And we have, this is the same as that, right? So let's just say that's x and that's x. And this is y, this is z, and this is 101, which is AB. Where this corner is A and that corner is B. Okay, I think that should be good enough. Using Pythagoras on that triangle, it'll be y squared plus z squared is x squared. And they are saying that y is an integer. So we have x plus z is 101, correct? So that means z is equal to 101 minus x. So plug that into there, and you'll get y squared plus 101 minus x all squared is equal to x squared. So this will be y squared is plus 101 squared minus 202x plus x squared is equal to x squared. And then the x squareds cancel, so then we get just 202x y squared plus 101 squared. And then if you isolate for x, you'll get that, which we can further sort of break up into 2 times 101. Okay, so now we have to figure out if x can be an integer or not, right? That's what they're asking. PD, which like this is P and this is D, so PD was representing, x is representing PD in my diagram. Okay, so can this be an integer? Well, let's see. Y, what are the properties of y? Y is an integer, right? They tell us that. Let's go back to the diagram. The length of BC is an integer. So the BC was denoted by y. And, okay, and BC, let's see here. Anything else that we're, AB is greater than BC, so that means AB, in our case, in this, AB is 101, so that means that 101 is greater than BC. So 101 is greater than BC, which I have denoted as Y. So Y is less than 101. Okay, so if Y squared plus 101 squared is divisible by 2 times 101, let's see here. Okay, I got it. Y, because of this property, since Y is less than 101, Y squared plus 101 squared is not divisible by 101, and therefore that means X will not be an integer. Suppose that BC is m for some positive integer m. Suppose further that for this value of m there are exactly 7 positive integers n, so that when AB is equal to n, the length of PD is an integer. Determine all possible values of m that satisfy m is between 1 and 100 inclusive. Let's draw that diagram again to remind you. Let's see here. So this was x, this was x. This is n, this is A, B, this was M, C, N minus X, and D. Okay, so, and that is the parameters, and using Pythagoras, x squared on this triangle, right triangle, right there, is equal to n minus x all squared plus m squared. And then when you expand this, you get x squared is equal to n squared minus 2xn plus x squared plus m squared. And then this would be 2xn is equal to n squared plus m squared. And if you isolate for x, you get n squared plus m squared over 2n. Okay, similar to the previous, this time we just have a whole bunch of letters. So our parameters are that m is between 100 and 1 inclusive. We have 7 solutions for n, and x is an integer. Yeah. Okay. Well, if we look at this guy right here, since n squared plus m squared divided by 2n is an integer, that means that it must be divisible by 2. So that means that n squared plus m squared is even. If it's even, then we have 2 possible scenarios here. We have either that n and m are both even, or we have possibilities that n and m are both odd. Okay, let's work with that. Let's go with this one first here. If they're both odd, then m is odd. So let's see here. Then I would basically be that this equation would become x is equal to n over 2 plus 1/2 m squared over n. Now, if x is an integer and they're both odd, let's see here. The only way that would work is if this is odd and this is odd. So that would basically mean that m squared over n is odd. Actually, let me go back and re-explain this. This is an odd integer, so this expression is an odd integer divided by 2. You got it? That's what I meant to say. It's an odd, so if, for example, if n was, whatever, 3, that would be 3 divided by 2. Now the only way this can be an integer is if this is also an odd integer, and therefore you would then be dividing by this 2. Does that make sense? So if m squared over n was whatever, let's say it's 3, then again it would be 3 over 2. So let me give an example. Let's just say m, let's say, is 45 and n is 5. And then x would be n divided by 2 plus 1/2 times 45 squared divided by 5. So this is 2.5 plus 45 squared divided by 5, I believe is 405 divided by 2. So then divided by 2 and then add 2.5. So this would become 205. So that's just an example to illustrate that if this guy is an odd integer divided by 2, and this is already a half, this has to also be an odd integer. So this is correct, that m squared over n has to be odd. Okay, so we got that. And then let's remind ourselves of the fact that m is, when you compare n and m, which one is bigger? N is greater than m, right? Because if you look at the diagram, this is n, this is m. And I think that was given somewhere up here. Yeah, way up there. So n is greater than m. Okay, I just got to make sure I make all these parameters correct. N is greater than m, and then therefore m squared would be m squared would obviously be greater than m just by itself, and then n is most likely in the middle there. So this is the inequality. Okay, got it. So then this thing here is really just m times m divided by n. And then now we have to really discuss this to explain it properly. They're basically saying that when you divide m by n, let me just go back and double check. Value of n, there are exactly 7 positive integers, so that ab is equal to n. ab is equal to n. BC is m. Okay, I got it. Let me explain this like with an example. Let's say you have m over n, and m has 7 divisors that are equal to n. Okay? My question to you is, if you have m squared over n, which is really what we're working with, then how many divisors are there? Divisors, number of divisors. Well, of the form n, how many? Well, initially it might not be obvious, so let me give an example to illustrate this. Let's say m was 10, right? And that's equal to 2 to the power of 1, 5 to the power of 1. Now, there's a formula that you guys may know that if you take any number and divide it into prime factors, 2 to the power of a, 5 to the power of b, the number of divisors can be calculated as a plus 1 times b plus 1. So in this case, the number of divisors would be 1 plus 1 times 1 plus 1, which is 4. Okay? And since there's so few, we can even list them, 1, 2, 5, and 10. But now I'm going to say, what if I have m squared? How many divisors are there now? Well, we can still do it. That would factor into 2 to the power of 2, 5 to the power of 2. And using this formula, the number of divisors would be 2 plus 1 times 2 plus 1, which is a 9. And really what that is this 4 times 2 plus 1. That's how you got that 9. So if this was 7, you would basically, let me write it in red, it would be 2 times 7 plus 1, which is 15. So 15 is the number of divisors for that scenario for m squared. So let me write that. If m has 7 divisors, n of the form n, m squared has 15 divisors, n. Okay. All right, I want to keep this in the same screen, so let me just bring all this up here now. Okay, so before we continue, we have to give a hypothetical scenario that m squared is, we have to factor it just like we created prime factorization over here. With an example, we have to create it in general terms. It would be some prime number to the power of 2a, and then some other prime number to the power of 2b. And I'm confident that there's only 2 prime numbers, because if there was 3, then the number would be much greater than 15. Like for example here, the number of divisors would be 2a plus 1 times 2b plus 1. So, and that has to equal 15. Got it. So how do we do? So either, for example, this could be 3, this could be 5, because 3 times 5 is 15. So if 2a plus 1 is 3, that means a is 1 and b is 2. Yeah. Or a is 2, b is 1. Either way, I mean, it doesn't really matter. So that basically means that you have a scenario where m squared is of the form some prime number to 2a, which would be 2, and then another prime number to to 2b, which would be 4. So therefore m would be p1 to 1 and then p2 to 2. Yeah. And then keeping in mind that m is between 100 and 1. So we have to find all the m's of that form. Okay, well, let's see here. And m is odd. That's another thing. So I can't put a 2 in there because 2 is an odd number, but because m is, we've made m odd, right? Yeah. Both m and n are odd. So let's try 3 as a prime number. And the primes obviously have to be distinct. So let's try 3 and 5. So 3 to the power of 1, 5 to the power of 2, or 3 to the power of 2, 5 to the power of 1. And if that's the case, this is what, 75. And this guy is 9 times 5, 45. Okay, that's in this parameter, that's in that range, so that's valid. What other combinations? How about 3 and 7? Let's try 3 to the power of 2. That'll be 9 times 63. If I do 7 to the power of 2, it'll be greater than 100 if I multiply by 3, so that's no good. And then with trial and error, I think I can get one more, 3 to the power of 2, 11 to the power of 1. That would be 99. So these guys will fit my parameters. Okay, so I got 4. All right, so those 4 I got as values of m. And what do they want? There's a determine all possible values of m. Okay, so I got 4 so far. Now I have to look at this scenario. So this whole thing was just if they're odd. Now I got to look if they're even. Okay, so I'll just keep that in there. Now we're looking at the scenario of when both n and m are even. And let's see what we get. So if n and m are both even, then what does that mean? It means that m is even. So m is of the form 2m, and n is even. So the small n is of the form 2n, big N. And therefore, if you go back to that formula, it would be, where's that formula? Right here. This one. It would be n squared plus m squared over n, 2n. So it would be m squared plus n squared over 2n. So if we substitute these guys, it would become 4 big M squared plus 4 big N squared all over 4n. And that reduces to just n plus m squared over n. And that's x. Yeah. And therefore, and let me put the parameters. M was between 1 and 100, and therefore the big M, since the big M is equal to half of the small m, that would mean that this is between 1 and 50, because they have to be integers. And very similarly, now we have the situation where m squared over n has 15 divisors, meaning m squared has 15 divisors n. So I guess that's what I meant to say. Very similar as before. So again, if we break it up into primes, it's going to be probably a first prime to the power of 1 to the second prime to the power of 2. And that would give me, when I square it, p1 squared, p2 to the power of 4. And then the divisors would be 2 plus 1 times 4 plus 1, which is 3 times 5, which is 15. And that works out. So it's going to be of this form. So, for example, if m was, let's say, 2 to the power of 2 times 3, that would be 12. And therefore m squared would have two to the power of 4 times 3 to the power of 2, and that the number of divisors are the 4 plus 1 times 2 plus 1, which is 5 times 3, which is 15. Yeah, that works out. And therefore, that 12 is a valid value for m, and therefore the value of the small m would be 24. And let's do one more. I'm not going to do them all. I'll let you guys do them. Let's do one more. How about if big M was 2 to the power of 1, 3 to the power of 2? That's 18. And let me just see if this checks out. M squared would be 2 to the power of 2, 3 to the power of 4. And the number of divisors would be 2 plus 1 times 4 plus 1, which is again 15. So that works. And therefore that M would be double that, right? Because small m is equal to 2m, and therefore m would be 36. Yeah. Small m would be, hold on, let me see if I did that right. 8, sorry, no, so 2 to the power of 1. No, that's correct. That's correct. I'm just getting a little confused between the small m and the big M. No, 36 is fine. So if you continue in this way, the values for big M that you will get are 12, 20, 28, 44, 18, 45, and 50. And then, of course, small m, which is what we're interested in, it would be 24, 40, 56, 88, the 36, the 90, and the 100. So 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11. So values are what satisfy the conditions of the question.